Okay, great. So this is about textbook, and then I think we can start. So our main goal of today first is to review the atomic models because I suppose you guys, all of you, have at least 1 year of honors camp. So this is why I think this is a review. And the major task is to talk about the Bohr's model and actually some advanced topic in the Bohr's model. So let's still take some time to briefly review the atomic model. And as you can see, it's called the evolution because you probably see, the as the time went on, the model is also evolving, right? And I think I can put a table here for you guys to take some time after class to summarize everything here. So what I should have, let's say the first one is the name of the scientist. Can I see it clearly, my writing? And also, is there a kind of serious lag when I'm writing and when you see, let's say my voice and my writing, is that kind of consistent?
Yeah, I thought it was.
Okay, good, good, good. Okay, and then it's the name of the model. Let's say model name. And then it's the typical experiment. And then let's say one more thing is the key point. Maybe the last one is the limitation. The limitation. So basically, there are 5 models, right? I will put the name here, and then you guys can take some time to finish the table by yourself after class. So the first model by Dalton, right, in the early 18th century, maybe we can just call it a Saphir model or a Bohr model, because basically Dalton think atoms are the smallest substance, the smallest particle, right, to make of everything, and it's tiny, and it's indivisible. Actually, now right now we know it's wrong, right? Obviously, Dalton had no idea about what are inside the atom. And then the next one is by J.J. Thomson, right? He discovered the electrons, the existence of electrons. So he kind of provided, 2 parts. So because overall is neutral. So if the electrons are negative, there must be something positive. So it's called plum pudding. I was told the plum pudding is not very popular in United States. It's kind of a UK breakfast. So probably doesn't make so much sense to you. But you definitely can Google, what does a plum pudding look like, right? Have a look at the picture, and then probably you will have a better understanding about what is the Thomson's idea. J.J. Thomson got Nobel Prize in physics uh, in the history of the Nobel Prize, kind of the early history of Nobel Prize. I believe is around 1903 or oh 04, right? The Nobel Prize started from 1901, so the first few. And J.J. Thomson worked in University of Cambridge, so he's a kind of a typical UK people. And next one is by the Roosevelt. Roosevelt actually is the student of J.J. Thomson. He discovered the existence of the nucleus. So we call this model into nucleus model. But you see, J.J. Thomson didn't really describe where are the electrons because he didn't know anything about electrons. So this is the next one. It just, prove the existence of the nucleus. There is a tiny, dense nucleus which carry most of the positive charges. And the next one is by Bohr, right? Bohr is, that is the key point we are going to talk about later. So what do you think will be a good title for the, Bohr's model?
Valence shell model or something?
Valence shell model. I think it kind of talk about the idea, but there is a kind of a relatively easy to understand name, which is called planet model. can you try to connect, the picture here with the planet, the name of the planet? So the kind of nucleus is the sun, right? And then the electrons in different energy levels are just like different planets. They have different orbit. So he also kind of raised the concept of orbit, right? The kind of the track of the electrons. Although right now we know it's incorrect. And then the last one, and also maybe we should say, so far we think this one is the correct one. It's kind of described some very complicated mass equation, the Schrodinger equation. We call it the electron cloud model, or we can say is the quantum mechanics model. Obviously, we are not going to touch too much quantum mechanics. So electron clouds makes more sense to us. So we use this kind of black dots to describe the probability of the electrons to stay or to show in a certain place. So we call electron cloud model. Yeah, so those are the 5 models. And then after the class, you can take some time to work on the other parts. Obviously here, probably you don't have enough space, right? I didn't leave enough space here. So for the experiment, I prefer you guys to provide either a figure or a scheme. So you can draw it by yourself. You can also kind of copy something from the textbook, right? For the Bohr model, maybe you can just draw something like this, right? And for the plum pudding model, if you read the book, I just want to give you an example. You probably see it's called CRT. What the full name of CRT? The last T is tube. CRT. It's kind of the old version of the television. Definitely much older than you guys. Right now, the television is kind of very thin, right? What is the full name of CRT? Give me 1 second. Let me check it.
Is it cathode ray tube?
Ah, yes, very good. So it's called cathode ray tube. So you guys can find the picture of the CRT, and then probably we have a better understanding about how did J.J. Thomson discover the electrons, right? So I'm not going to talk too much about this part. I think this is something very easy. Even if you didn't learn it or you forgot, you can just take some time and quickly pick them up. So for each of them, add a picture, CRT. Yeah, I believe there will be a good picture for you to put it here. Let me quickly show you. CRT electrons, maybe that should be enough. This is a little bit complicated. We can add like J.J. Thomson. Yeah, basically something like this. So when you have enough space, you can add a picture like this to be there, right? So basically you have a electric field, and then the deflection of the electrons kind of demonstrates it carries some negative charge, right? So for all of the other models, find a picture similar to this, which can better help you understand the concepts, okay? For the key points, you don't have to write down a lot of sentences, just add some bullet points, right? For example, for the plum pudding model, so there are electrons. This is the first one, right? The second one, electrons are negative, right? I think this is the major part we can get from the J.J. Thomson's model. But obviously, Thomson kind of did some other interpretation. He thought the distribution of the electrons are kind of very even, in the atoms. So this is why, you saw the negative charge kind of evenly distributed, over the whole atom, right? Definitely there are a few other stuff, but they are not so important. Okay, I think you guys are clear about what this assignment, and you can also pay attention to the the scientists who made the contribution, like Dalton, J.J. Thomson, Rutherford, Bohr, de Broglie, and Heisenberg, Schrödinger, because the last three kind of, and including a few others, like Bohr, they all made a contribution to the electron cloud model. And in the bottom of this page, I also listed a few kind of important discoveries in atomic structures with the year, the scientist, and the discoveries. So you guys can also have a look. I think you probably realize in the earliest 20th century, 1901 to 1913, maybe 1920, that is a kind of decades or maybe 2 decades with so many great scientists, right? they all got Nobel Prize pretty much, right? So this is really, some amazing years. Okay, then let's start, our stuff. The hydrogen's emission spectrum, right? You guys probably already kind of familiar with this kind of picture, which is the results of the hydrogen's emission spectrum. But first, we need to know what kind of device is to give the results like this. Actually, it's called a hydrogen discharge tube. Let me briefly, show it here. So basically, you have a glass tube, and in the glass tube, there is hydrogen gas. So the full name, and then this tube is connected to an electric field, right? Or, in a circuit, let's say in a circuit is more accurate. And then we call it hydrogen discharge tube. I think you guys understand the meaning of discharge here, right? So basically, you want to excite, the hydrogen molecules, the atoms. And then the result is you will see a certain color of light is emitted. So you have the light emitted. Most likely it's kind of, bluish purple. We can, have a look. Hydrogen emission spectrum. Yeah, something like this. In the left part, you probably can see, it's a little bit bluish purple, but right now there is a kind of a strong background color. You probably cannot see it so clearly. I think this one probably, give you a better sense about what is the color. So what exactly is the color? Actually, after we use a prism to separate, the light to give us a better resolution, what we can see is like this. Actually, there are 4 distinct lines, but it seems like you can only see 3 of them. There is another one, which is here, kind of relative close to the purple one, is a little bit, light here, but there are supposed to be another line here. So basically, you should see 4 lines by using our eyes, the human eyes, which is the visible range. If you have the equipment, you will see a full spectrum like this. This is still the hydrogen's emission spectrum. So you probably see the 4 lines, actually more than 4. In this area, we call it the Balmer series because they are all in the visible range. This is the lines we can see as human. But there are also another group here with a wavelength, less than 200 nanometer. Pay attention to the unit, is nanometer. 1 nanometer is 10 to the -9 meter. So it's pretty short, right? And later we are going to discuss actually all of those lines are in the ultraviolet range. They are higher in energy, but shorter in wavelengths. And then there is also another group here with longer wavelengths. Typically, they are longer than 800 nanometers or 700 nanometers. They are in the infrared range. They have lower energy and longer wavelengths. So we also got two names. One is called Chen. I'm not sure whether it's really called Chen or not. Maybe it's just Chen. Maybe Chen is a good pronunciation. And the first one in the UV range is called Lyman. So you got three names. Balmer. This is just to name the scientist who discovered the series. And Balmer, very interesting. He is a elementary school math teacher. So you can see at that time, everyone can kind of be a scientist. So I want to emphasize, typically when we are talking about visible light, we are talking about 400 to 700 nanometers. So if it's shorter than 400, it's ultraviolet. If it's longer than 700, it's infrared. So based on this, can you think about what will be the wavelengths of the red light and the purple light, respectively? The red light will be close to 7 or 400.
700.
Right? It will be 700, right? Because longer than 700, it will be infrared. So this side is the red. And then shorter than 400, it will be ultraviolet. So this one will be purple, right? Or violet. Okay, so before we talk about how did Bohr really explain the hydrogen's emission spectrum, we want to differentiate a few concepts. The first one is line spectrum versus continuous spectrum. So based on the name, can you tell me, which category is the hydrogen's emission spectrum? Is it a line spectrum or a continuous spectrum?
A line spectrum.
Yeah, it's very obvious, right? This one is a line spectrum. So how does a continuous spectrum look like? It's just the white light. If you use a prism to separate the white light, the sunlight, you will see, the rainbow, right? From red to purple, red, orange, yellow, green, what's next? Blue and purple, right? Yeah, that is kind of the continuous spectrum. And then there's another concept called emission spectrum and absorption spectrum. Based on the name, emission means it emits photons, emits light. Absorption means, it absorbs light. So I want to briefly describe, the hydrogen, I already called it emission spectrum. And let's suppose we don't know it's hydrogen's emission spectrum. Let's say it's hydrogen spectrum temporally. So as you can see, first, it has a black background. Secondly, there are several, several lines appeared. So based on these two characteristics, I think we can easily conclude what is the emission spectrum, and we can also easily conclude the hydrogen spectrum is emission spectrum, because black background means no other background light, so it only have a few kind of lines emitted, right? So based on this, can you guys think about how does a absorption spectrum look like in terms of these two perspectives? First, how about the background? Is this still a black background? So emission absorption spectrum is based on, the input light is the white light or the sunlight. So you should have a continuous spectrum as the background versus a continuous spectrum as background.
I have a question.
Right?
What does the background represent? Like,
it's here. Can you see, everything except the few lines are black? So basically, when you, measure the spectrum, you will see the majority of the light is either absorbed or either appeared. Let me show you a picture and then we can summarize the difference of these two. So emission spectrum, actually, this is a good question, versus absorption spectrum. I think this is good, a good way to demonstrate the idea. It seems like I cannot make it larger. Let me see. Okay, now it's good. So as you can see, here is the difference of the emission spectrum and the absorption spectrum. So now I think, can you realize what is the meaning of the background, right? So in the emission spectrum, everything is dark except the few lines, which means only in those specific wavelengths there are light, emitted, but all of the other wavelengths are kind of dark. There's no light. So the whole spectrum is from either longer wavelengths to shorter wavelengths or shorter wavelengths to longer wavelengths. Basically, if we are talking about the visible range, we are talking about 400 to 700. But I think you guys can figure out which side is the 400, which side is the 700. The 400 is supposed to be in the right side, right? Because it's purple. And the 700, the longer wavelength, is supposed to be in the left side, which is red, right? So this is the meaning of a spectrum, so the first one, emission, black background, and a few lines. And the second one is the absorption spectrum, which means the input is I think it's supposed to be the sunlight, but if the high density hard matter, it should also produce the white light. The white light can give you a full spectrum from red to purple, right? And then you saw there are a few black lines, which means those wavelengths of light are absorbed by the substances. So this is why it's called absorption spectrum. And actually, as you can see, what is the relationship of these two spectrums? Pay attention to the location of those lines.
They're
Can we say,
same.
Yeah, there is a word in AP Chem called complementary. So complementary means if you add these two together, it will give you a full spectrum, right? So the lines are corresponding to each other. So this is exactly the relationship between the emission spectrum and the absorption spectrum of the same substance. And later we are going to further explain this, why they should have a relationship of complementary, right? So if you want to take notes, I will recommend you do something like this. So for the emission spectrum, we can have let's suppose this means a black background, and then we can draw a few lines, red, blue. I think I can find more color. Purple, which should be here. And then let's say orange is here. I think several lines should be enough to show the general idea. And then for the absorption spectrum, it's slightly harder to draw because it's not easy for me to show the full spectrum. What I can do is kind of draw a few lines, which means those lines are absorbed. And then I will try to maybe there is another function for me to Is this one better? Question. Okay. But this is a little bit, challenging for me to find all of the colors. So just to show a general idea, okay? So for this range like this, for this range is blue, and for this range is purple. And then you guys can add the other stuff. Just want to show a full spectrum. Although the full spectrum is really not like this, kind of the colors are separated because it's a transition, right? There is a transition. So if you see something which is very red, probably you will see it's like purple. And then if it's even, darker, it might be like black, right? This is kind of, when our human eyes see the different intensity of colors, it will give you different results. So this is a transition. It's kind of a full spectrum. You couldn't see really, there is a boundary between two adjacent colors, okay? So I think let's finish, the summary here. The first one, the background, is a continuous spectrum, or I should say a full continuous spectrum. The second one, there will be a few lines black or missing, right? Which means those, lights with specific wavelengths are absorbed. So obviously, hydrogen's spectrum is a emission spectrum, right? Okay, so the key question is here. How did Bohr's model explain the hydrogen's emission spectrum? This is a little bit complicated, I have to say. And actually, this is also a challenging, topic in AP Chem, because most of students do not have too much physics background when they are taking AP Chem. And actually, since it's related to light, right? There's always a lot of physics behind that. So today, we are not going to teach you a lot of physics, but if it's related to the physics, I have to briefly, explain the physics behind that. The first concept is called quantitized energy. So there's a kind of picture to demonstrate the idea. So the right one is kind of, the energy can be any value. There's kind of, you can, the man can stop at any place and to provide or to give a specific potential energy. But, it's a continuous manner, right? You can stop at any place. So basically like a number. So now say, how many numbers in between 1 and 2? I asked my daughter, who is a first grader about this question. She told me there's no number. There's no number between 1 and 2. But obviously, we know there is kind of unlimited, numbers between these two. So this kind of give you a sense of what is the continuous manner. But if a man is climbing, the floors or a ladder, let's say a ladder maybe makes more sense. So he can either stop here, or stop here, or stop here, or stop here. He cannot stop, something in between. So this concept is called quantitized, which means, there is a small unit, and you cannot make this small unit even smaller. So which means, let's say if this is the smallest unit, so the height is made by an integer number of this kind of small unit. You cannot say I have 1.5 packets of energy like this. You either have 1 packet or 2 packets, and 1 packet has a certain amount of energy. So which means the energy is not continuous, it's quantitized. So there is a smallest energy packet. So which like the idea here, either here or here or here or here. You cannot stop, in the middle, right? Your feet must step on a certain level. So this is called quantized energy. So this is the first concept. Energy is not continuous. But it seems like we can say, the energy is 1.1 joule, 1.11 joule, 1.111. We always describe the energy in this way, right? So what is the smallest, packet of energy? Actually, is a very, very small number. So the smallest energy packet is described by h times nu. So the h is the Planck's constant, which is 6.63 times 10 to the negative 34 joule second. So as you can see, the magnitude of this, energy packet is so small. So this is why typically we will not pay attention. We kind of think energy is continuous, but actually it's not. This is a little bit hard to understand, but from the goal of our USNCO or AP Chem, we don't really understand at the same level in AP Physics or the class beyond. So that should be enough. The second group of concepts is called ground state and excited states. I think this is relatively easy to understand. So now say you have 2 floors in your house. So your ground state is the first floor. And in the night, you probably go to your bedroom, which is in the second floor. And then we call you are in an excited state because your potential energy increased, right? You have a higher potential energy when you are in the second floor compared to on the first floor. I think this makes sense because when you are in the first floor, you have lower energy, you are in a safer place. Let's say if you go to a higher place, you have a higher risk to fall down, right? That means you are in danger. You are more dangerous than you are in the ground state. So this is the difference between ground state and excited state. Basically, what I want to give the sense to you is ground state means stable. Excited state means unstable. And ground state means lower in energy, lower E. And excited state means higher energy, higher E. Does this make sense to you? Okay. And then another concept is called binding energy and ionization energy. I think you probably already learned what is the meaning of ionization energy in your previous chemistry class. Can someone briefly talk about what is the meaning of ionization energy?
It's like the energy required to take an electron away from an atom, and usually it's a lot higher for like something like chlorine, which really needs its electrons, or like a
Very
noble
good.
gas.
Yeah, very clear and very accurate. So basically, if we want to make it more specific, we should say it's a kind of gas state of a atom. A means any atom. When it loses 1 electron, how much energy is needed? Obviously, when it loses 1 electron, it will produce a cation with 1 positive charge. So this process definitely is endothermic because the electron lost previously was absorbed by the nucleus, right? So this is called ionization energy. So what is binding energy? Basically, is the same idea. It means how strong does this electron is attracted by the nucleus. So I think you realize binding energy and ionization energy are talking about the same stuff, but in a different way. Ionization energy is take the electron away, so it need to absorb energy. Binding energy is how strong it is, attracted. So typically when we say binding energy is negative because the electrons are negative, the nucleus are positive. So the attraction between a positive charge and negative charge are typically expressed in a negative way. That is just the way for you to describe it, but they are pretty much the same. And then Bohr used the idea from the previous scientists, including Balmer, and raised, a energy level diagram like this. This is the key point. First, he thinks the electrons are located in different energy level. So basically, if the nucleus is here, and then the electrons can either surround the nucleus in different, way, in different place. So this is called the first energy level. It's called n equals to 1. This is called the second energy level, n equals to 2. This one is called the third energy level, n equals to 3. So this is the first idea, energy level. The second idea from Bohr is the concept of orbit. He thought the electrons are surrounding the nucleus with a very clear, track, a clear path. And orbit, the concept is used to describe the movement of the planets in the solar system, right? But actually, he used he borrowed the idea and applied into the, hydrogen structure. Orbit, right now we know is incorrect, okay? They have an orbit. And the third concept is the ground state versus the excited state. I will make it slightly easy. So the electron will prefer to stay in n equals to 1 because at this moment, it has the lowest energy. And then if it absorbs energy, it will be excited. Obviously, it will have higher energy. That you can see, we describe the value of the energy here. So when n is equals to 1, the energy is negative. Don't forget the negative here. 2.18 times 10 to a negative 18 joule. Obviously, you don't need to memorize, the value, but give you a sense. First is negative, secondly is very small, right? And then when n is 2, I think you can see the absolute value is getting smaller, which means the energy itself is getting higher, right? Make sense? And then if it goes up, it's even higher, right? So we call here is the ground state. And then all of the others are excited state. They have higher energy, they're relatively unstable. So if the electrons stay in the excited states, what will be the next step? Will the electrons feel comfortable when they are staying there? The electrons are just like human beings, right? They want to be stable. They want to be more comfortable. So this is why they will transit back. They will transit back. And their final goal is back to the ground state. And later we are going to talk about, how those kind of transition from an excited states to the ground states will produce the hydrogen emission spectrum.
Why is the energy negative again?
Good question. I should say about this. Yeah, this really depends on how we define the zero level. For example, if we want to describe that called altitude, like how high a certain place is, it's called altitude, right? So we define the sea level is 0 meter, right? And then the height of the Everest is, let's say, 8,800 something, right? But if we change another way, if we define the peak or the top place of the Everest mountain is 0, and then you will describe the sea level is negative 8,800 meters, right? So right now, our reference, our 0 level is here. So which means when n equals to infinite, what does it mean? So basically, the electron has no relationship with the nucleus anymore. Basically means the electrons is gone. We describe, this place has a 0 energy level. That is 0. So this is why when it's it goes closer to the nucleus, the energy is getting lower, and then this is why it's negative. And also the negative is related to is a attraction between the positive nucleus and the negative electrons. Typically, we call this kind of different charge, different sign of charges into negative. So basically, it really depends on how you define your zero. If you define your zero here, you can say this place is 2.180 times 10 to the negative 18 joule. So it's the same. But we got used to, here is the zero level. So, and it's also called a free electron, So if we review our concept a little bit, so if the electron is here in the ground state, so can you tell me what is the ionization energy of this electron? And what process is corresponding to the ionization process? I think we can say the electron transits from n equals to 1 to n equals to infinite. This process is the ionization, right? Because basically means totally remove the electron away and make the electron has no attraction, no relationship with the nucleus. And now I think we can easily tell what is the ionization energy of this electron. That is the energy difference between the zero level with this value, right? A very good question. And then how can we get, the values like this, right? They are not integers, they are very weird. So here, Bohr raised the equation. This is very important. En means the energy of electron when the electron is in a certain energy level. So n can be 1, 2, 3, 4, 5, right? All of the positive integers. And then is equals to negative RH over n squared. RH is a constant called Rydberg's constant. What is the full name? Rydberg. Obviously is the name of a scientist, and it doesn't matter. And the subscript H means this constant is for hydrogen atom. If it's not hydrogen atom, maybe it's different. Okay. And then the n here is the positive integer 1, 2, 3, 4. Okay, give you a few seconds for you to think about, can we use this equation to match the values in the left side, in the y-axis? I think you can even calculate what is the value of the RH, right? Yeah, I saw a lot of you, knocking your heads, which is good. So I think we can calculate RH should be 2.180 times 10 to the negative 18. What should be the unit of the constant?
Joules, or
should be joules, right? Joules, right? Obviously, here is the energy for n equals to 1, right? So this is the Rydberg's constant. Obviously, we don't need to memorize this. So far, this constant is not in the test paper of any USNCO. So I don't think we need to use this constant for calculation. But our class, this class, is built on a level slightly higher than the national Part 1, slightly higher than that. So we might have a few questions which requires you to use the constant for calculation, but the constant will be provided, or you can find it by yourself, in Google or search online or on the textbook. Okay. So the reason why I keep the level slightly higher than Part 1, first, our goal, as I mentioned, in the info session, definitely is to prepare you first to excel in the local exam, right? But I try my best. You also need to work from your side, right? No matter how strong I am, but if you don't have enough time, to take the class, practice the problems, review the contents, it might not enough, right? And national part one has a very similar to style with the local, but it's I should say it's harder, but not much harder. So if we kind of aim at a level of slightly higher than part one, which means you probably can also aim at the part two, but it's just a different style. Part two are all written questions, right? So this is why students feel part two is much harder than part one, because solving multiple choices are definitely much easier, right? You don't need to show your work, right? And sometimes you can use the method of elimination, right? You can easily kind of eliminate one or two options. So sometimes you can guess, although you are not very sure. And for most of the time, your guess is right. Right? Okay. I think probably you can see a few more stuff behind this, energy diagram. The first, what is the pattern of the gap between two adjacent energy levels? When N is increasing, how about the gap? You guys know what I'm talking about, right?
Yeah, it's like
That increases, they decrease.
Yeah, when N is increasing, the gap is decreasing, right? Let me use a certain way to describe the idea. So a few more advanced, conclusion. Those are some fundamental stuff about the energy level diagram. The first one is N. When N is increasing, the gap of the energy between N versus N plus 1 is decreasing, right? Or you can make it into En plus 1 minus En. It's pretty much the same. Let me see. Any other stuff? I think this is the major one. Yeah, this is the major one I can think about. Okay, yeah. So we talk about the first equation here. There are two more, equations here. I'm not sure whether you guys are familiar with these two equations or not. The first one is called delta E equals to H times nu. What the idea? So when the electron is here, is in the excited states, it's unstable, it wants to be stable, it will transit back. But there is an energy gap. So based on the law of the conservation of energy, the energy difference must be shown in a certain style, right? So this kind of energy difference will change into a photon, or you can say a light with a certain energy. And the energy of the light is supposed to be exactly the same as the gap. Does this make sense to you? Based on the law of the conservation of the energy? Because energy is decreased, right? So it must change into another style, which is a light. Light is a wave of energy. So we say the delta E equals to H times nu. H, we mentioned before, is a constant called Planck's constant. And nu is something called frequency of a wave, because light is a wave. Frequency. I will talk about the exact meaning of the frequency in the next page. And there's another equation. Nu is still frequency. Lambda is the wavelength, kind of how long is each wave wave packet, and c is the speed of light. Is also a constant. You guys probably know the speed of light in the vacuum is very close to 3.0 times 10 to the power of 8 meter per second, right? A little bit, physics give you an idea. I think you see, two different waves. They are different color of light. Let's use this to briefly talk about what is the wavelength. If we start from here and we end I think we end here, right? Am I right? Maybe I should start from here. Let's say this is kind of the 0 level. So I start from here and go to another place here. So basically it's one up and one down, right? This is called a wave. This is the length of the wave. I prefer to draw it by myself. Yeah, this is called the wavelength. This is positive, this is negative. So all of the waves are like this. So now say you have a rope and you do it this way. You probably see something like this, right? Like it's not like the snake, but you see the transfer of the wave and pass through the air, right? That's kind of made by, I should do it this way, right? And then you see this kind of up and down, up and down. So this is called the wavelength, the length of the wave. And then obviously, if we compare these two, can you tell me which one has a longer wavelength?
Like at the second energy level.
Yeah, obviously the second, right? The B one, right? Has a longer wavelength. And then the next one is the frequency. Frequency means how many waves passed through the space in a certain unit of time. So that's it per second. So in 1 second, how many waves passed it? Because the waves are kind of transferring, right? So that is called frequency. But based on this picture, we cannot really tell, what is the frequency of each wave. But basically, how many waves pass through in 1 second. So what will be the unit? This is the wavelength called lambda. What will be the unit of the frequency?
Hertz or seconds, like inverse seconds, kind of.
Yeah, I got something called hertz. But hertz really didn't tell us the exact meaning of frequency. So I prefer you use per second. So basically it's how many waves per second or per minute or per hour or per year, right? But for a light, typically we use second. So how many stuff, there's no unit for the stuff, right? How many wave packet or how many waves. So this is why it changed into, per second. But it has the same meaning as hertz because hertz is defined as how many per second, the number per second, right? This is frequency. So you probably see something like F in physics to represent the frequency. But in chemistry, we prefer to use nu. And this is not V, this is a nu. Very interesting. This is a Greek letter, I believe. It has a pronunciation like new, new. And the writing is also slightly different from the V. The V, so maybe the open is a little bit larger, right? It's very hard to differentiate from the handwriting. But if you have a look at this one, new frequency. I should say add a symbol. Yeah, it's something like this. It's quite similar to the V, right? Quite similar, but slightly different. Just pay attention. It really doesn't matter, you know. What do you write? At least you understand. This is not the velocity; it's the frequency. Okay. Yeah. So let's write down the two equations. The first very important equation is energy of a light is proportional to frequency. Not related to any other stuff, just related to the frequency. Secondly, lambda times frequency equals to C. I do not recommend you to try to remember this equation. I prefer you can try to understand it by yourself. First, lambda is the wavelength, the length of the wave. Nu is the frequency, is how many waves pass through a certain point in 1 second. So if you multiply these two, the length and how many per second, what do you get? You get, you know, what is the speed of the wave, kind of how fast does the wave is transferring in a certain space. This might be a little bit tricky, guys. Let me know if you have any question. I can further explain. This is pure physics, but this is something fundamental. We must know it, you know, in USNCO, in AP Chem. Otherwise, we cannot continue. So it gives you the speed, and the speed is a constant. So we got, you know, a few important conclusions. The first one, longer wavelengths means, how about the frequency? Since their product is a constant.
It's a lower frequency.
It's lower frequency, right? And lower frequency means, how about the energy?
Lower energy level.
Yeah, lower energy, right? Lower energy. So now let's talk back to the visible light from 400 to 700 nanometer. This is red, this is purple. So now can you think about which color of light has a higher energy by using these two equations? My question is, which color of light has a higher energy? The red one or the purple one? Yeah, it must be the purple one, right? It has a shorter wavelength, which means it has a higher frequency, which means it has a higher energy. Do you need to memorize this? No, because based on your life experience, you already know UV light is harmful. Why is it harmful? Because it has
too much energy.
Exactly, right? If you go to the beach, you do not wear sunscreen cream, your skin will be burned, right? Because, you know, there are just too much UV light, and UV light has higher energy. The energy is high enough to excite, to ionize the electron of the atoms in your skin. So think about, if the atoms on your skin lose the electrons, the bonds are broken. So the proteins, the nucleic acid are broken, and then skin cancer, right? So this is why UV is bad, right? So this is why we need to use sunscreen cream to protect you, because the cream can either absorb the UV light or kind of transmit the UV light. Actually, it includes both ingredients. And I think Alex probably remember, we had one student who did the research in improving the sunscreen, right? Sunscreen materials.
Oh yeah, I remember. I remember.
Yeah, by adding different stuff to the sunscreen, right? To increase, to improve the efficiency, and also to decrease the pollution. And obviously, in this side is the IR, we never heard about IR is harmful, right? And actually, during the pandemic, we even used the infrared kind of thermometer, right, to kind of measure the temperature, the body temperature. And we also use IR for imaging, right? That is called the thermal imaging. So basically, there's not necessary to have visible light. So even in the dark, in the night, we can still use the IR to make pictures. That's because all of the live animals, they are producing heat, right? And this heat actually is in the wave of infrared, right? If we continue, you guys know, if the energy is even lower than IR, what's next?
It's like X-ray.
X-ray is in that side. X-ray has very high energy because, yeah, you don't want to be exposed on the X-ray, right? Yeah, right. It's microwave, right? That is something we used for the microwave oven, right? And later, we are going to briefly summarize how does each of the electromagnetic radiation, such as UV, visible, IR, microwave, interact with the matters. Kind of basically what is the function? How does the microwave oven really work? How about even lower in energy than microwave?
Radio.
Exactly, that's the radio. This is something we used for communication, right? The Wi-Fi, the 4G, 5G, those kind of stuff, right? And you probably heard the debate of the 5G. So someone mentioned 5G can give you fast speed, right? So we might have what that called auto driving. We don't need to have a driver anymore, right? Because we have fast speed to communicate with the central place, right? And we might have remote surgery because the speed is fast enough to the for the doctor to see the patient in a different place, right? But we also see a lot of concerns about the 5G because actually 5G use a slightly shorter wavelength compared to the 4G. And shorter wavelength means higher energy. So this is why people start to concern the radiation made by the 5G. But if you think about, there are so many people who go to the beach without wearing sunscreen cream, and they are worrying about the 5G. This is just ridiculous. But obviously there is still something different, because for the 5G, it's put in your phone, and you are going to carry your phone in a very close distance, right? When you are asleep, when you're sleeping, you put your phone probably very close to your head, to your brain, or you carry your phone in your pocket, right? 24 hours per day, probably, right? That is the another concern because of the distance issue. How about this side, guys? You mentioned about X-ray, right? So the next is X-ray. I have no space. I put it here. So every time when you need to have what that called? It's called CT, right? You use the X-ray to take a picture of your bones, right? That is harmful to your body. So this is why you need to wear the very heavy lead, clothes, right? To protect, the parts you don't want to be exploded, under the X-ray. I think you have the experience, right? You need to wear a very, very heavy, clothes, which is made by lead, because lead is a heavy metal with a very high density. How about something even higher energy than X-ray?
Gamma.
That's the gamma ray, right? The gamma ray. Yeah, gamma ray can even used for surgery, because just like a knife can cut your body, right? Okay, that's a kind of general idea, and these two equations are very important. And now I think you understand what we are going to talk. So if the electrons are here compared to the electrons are here, they are both excited, right? They are both excited, and now they want to transit back. They want to go to the ground state, but the energy gap is different. N equals to 5 back to N equals to 1 obviously has a higher energy gap. So this is why it emits light with a shorter wavelength and higher energy. And for 2 to 1, the energy gap is smaller. It emits a light with longer wavelength and lower energy. Does this make sense too? Okay, good. So now it's your turn. So now we are going to explain the 4 lines in the hydrogen's emission spectrum. So can you try to finish these 4 blanks by yourself? So Ni means initial. Nf means final. So just a reminder, you may need to have a look at the N final here and double check this. That give you 1 to 2 minutes. If you guys have any question, feel free to ask. Okay. Let's say you have a question in how to interpret the picture here. Yeah, it seems like most of you are pretty much done. Give you a few more seconds, 10 to 20 seconds, to figure out, what is the initial of each line here. I think this is pretty straightforward, right? Actually, this reminds me a joke in mathematics. It's not really about mathematics. It's kind of the evolution of the level of mathematics in United States. So back to like 1980s, the question probably like this. So ask you to calculate the area of the left parts by providing, the length here, the length here, the radius here, right? Obviously, it's quite complicated. And then the next one turned into, maybe I should put it here. This is the first level. The next level is easy. Calculate the area here by providing the length, the height, the width, right? And then the next level, let me see. I turned into a multiple choice. A, let's say, is 30, B is 40, and then CD. And the next level is, what is the name of the shape of this stuff? Is a square, is a rectangle, is something? And the next one turned into, use your favorite crayon to color this stuff. So this is a joke. This is called the evolution of the math education in the United States. So I hope you guys are not kind of, Okay, back to this. Edward, would you like to have a try? So what is the red one?
The red one and initial is 3.
Mm-hmm. How about this one?
The blue cyan one and initial is 4.
And obviously this is 5 and 6, right? Not hard. But I think now finally we can have a little bit, further explanation about the hydrogen's emission spectrum. First, we can explain why is emission. That's because when you use the electricity to excite the electrons will jump from, the electrons are here initially, will jump to different energy level, to here, to here, to here, to here, right? They will jump to different energy level. This is the process of excitation. And then they will transit back. When they then transit from 6 to 2, they emit a relative, higher energy of light, which is the purple one. And then if from 5 to 2 is the blue one, is 4 to 2 is this one, and 3 to 2 is this one, is the red one. Those 4 lines are in the visible range. I think we explained first why is emission, secondly, why there are 4 lines, right? But there is another question for you to think about. Let's take a very brief break, 5 minutes of break. Just want you guys to stretch yourself a little bit. Go to the restaurant if you need. Sitting here for 2 hours definitely is tough, right? Yeah, take a break. I will see you guys at 9:25. Okay. Yeah. See you guys later. Okay, I hope you guys are back. Now restart. Oh, by the way, how did you guys feel? How about the pace, the difficulty? Feel free to let me know, what's your idea, okay? You can either, send message to me, privately or publicly, it doesn't matter, okay? You can, feel free to jump in and just, talk about your feedback. You want to be a little bit faster or a little bit slower, and or, you have question about anything, okay? Since, we are a relative small class. To be honest with you, I think we can make it a really a really good class. Okay. Question. So the first one. Well, how about those transitions to n equals to 1? If the n final is 1, where are those transitions? It should have much more than 4 lines, right? Any idea from you guys?
Is it 5 lines or?
Actually, there are more than 4 lines, but we can see 4 lines relatively clearly. So I'm asking about, for example, where are those lines about now 6 to 1, 5 to 1, 4 to 1, 3 to 1, 2 to 1? Where are those lines? Even 7 to 1, right? There are supposed to be a lot of lines, right? Why there are only 4 lines here?
Aren't those lines in a different series?
Which series? It might be in the UV one or in the IR one.
I think Paskin or something. I don't know how to say it. That's n equals 3, and then Lyman is n equals 1.
Why Lyman? Lyman is in the UV range. So why Lyman is n equals to 1?
Because that's going to be the most energy. Because there's more.
Exactly.
There's
Right?
more levels, so it has the most energy.
Yeah, the energy gap between n equals to 1 and n equals to 2 is the biggest, right? So even if it's 2 to 1, it seems like it's the smallest energy gap for the NF is 1, right? That's already enough to make the transition into the UV range. So all of the n equals to 1 will be in the Lyman series. How about n equals to 3? So which means everything back to 3. That will be in the IR range because the energy is not enough, right? So if we go back a little bit, obviously the full spectrum, the spectrum should include many more lines. We just show part of them. But now I think we can explain Balmer is basically n final equals to 2. And Lyman is n final equals to 1. Hey. So bad. Hopefully we can survive until the end. And the Passion is NF equals to 3, right? And actually, as you can see, there are more lines in the visible range, right? But since they are so close to 400, and a few of them are even smaller than 400, so it's kind of a little bit beyond the human eye limit. We cannot see them clearly, right? Because if it's UV, we just cannot see it. So this is why you see 4 lines typically, but there are a few. Where are the other few? Basically, I think it's the second question. How about we talk about 5 to 2, 4 to 2, 3 to 2, 2 to 2. Not 2 to 2, 5 to 2, 4 to 2, 3 to 2, right? And 6 to 2. Those are the 4 lines. I made a mistake, guys. I think this should be 2. So where are the lines from n greater than 6 to n equals to 2. Now say 7 to 2, 8 to 2. They are here. They are here, right? Although they are not so visible, but they are there. So next, I would give you an example of calculation to show you why. Now, so let's take 3 to 2, for example, to show you 3 to 2 is in the visible range and is supposed to be very close to 400. Okay, let's have a try. You guys probably need to, have a piece of white paper to take some notes because I don't think there is enough space on my lecture notes. It's already very thick, right? For so many pages already. So we are talking about n equals to 3 to n equals to 1. First, the energy here equals to negative RH minus 3 square. And the energy here equals to negative RH over 2 square. So we can calculate the delta E should be RH times 1 over 2 square minus, I think, let's make it, more accurate. So equals to negative RH and then 1 over 3 square minus 1 over 2 square, right? And the RH value, if you check, it should be 2.718 times 10 to negative 18 joule. You guys can correct me if I, remember it wrong. And then we put the value in. With the unit. And then we calculate this part. Obviously, we can use a calculator. Oh, by the way, you guys always need to have a scientific calculator with you, okay, when you are taking the class. Do not use your cell phone. This is really a bad habit. First, you need to make friends with your calculator. For example, if you are taking no matter the local or the national, first, your iPhone or your phone are not allowed to bring, right? Secondly, if that is the first time for you to use a scientific calculator, it's very easy to make mistakes. Trust me. You need to make friends with your calculator and do not change your calculator. Use the calculator all the time, the same one, the same style. And then you are familiar with all of the keys, all of the functions. Make sure you want to press 2, it will not be 3, okay? Otherwise, it's very easy to make mistakes.
I think the Rydberg constant is 2.180.
Okay, 2.810.
2.180.
Okay, thank you. Like this, right? Thanks.
180.
What I'm doing. 180. Yeah, so have your calculator. And then, can you guys let me know what is the result here? It should be negative, right? I think it should be enough, right? 4 significant figures. Although it should provide unlimited significant figures, but since the constant has only 4, so 4 should be enough, right? So you got 3.028 times 10 to the negative 19 joule. Am I right? Please confirm for me. And then we know delta E equals to h nu, and nu times lambda is the speed of light. So we can put h equals to h times nu should equals to c over lambda, right? So we put this in the equation. We got this. Is this relatively easy for you guys to follow, or is not so easy?
Because, yeah, I think it is.
Good. Because most of students took chemistry before physics, but in regular chemistry classes, typically teachers will not guide you to do mass like this, and they will not show the work on the board for most of teachers, as I know. But this is very common in physics. But unfortunately, most American students take physics, in their 11th grade, 12th grade, and a lot of them even do not take physics in high school. Okay, and then we can put all of the constant in. This is 6.64. It is correct. It seems like this is not correct. My memory is getting, worse. I'm getting older. I forgot. You guys can double check for me. What is the exact value here? What I'm doing. I'm sorry, guys. Because we want to calculate the lambda, right? So the lambda equals to hc over delta E. And now we can put everything in because we already calculated delta E, and we know H, we know C, times joule second. No, meter per second. Meter per second over delta E, which is here. Yeah, can you guys confirm for me? I didn't make any mistake. And also the constant of the Planck, is this
Planck constant is 6.626.
Yeah. Thank you. This makes more sense. I think the others are correct. Okay. Now we can, confirm the unit. So joule is gone, right? Second per second is gone. What do you have? You have meter left. This is something we are looking for, right? Because meter is supposed to be the unit for the wavelengths, right? Or we can change it into nanometer later. So now we need to further use our calculator. Personally, I prefer we do something like this. Rather than put everything directly in the calculator, I prefer you guys choose this part in your calculator. And then for the magnitudes, and then you can do another part of, using calculator or just to use mental math. It depends on you, okay? So let me try. This will save you a lot of time and also avoid, the possible mistakes you might to put when you are using the calculator. So I got, it seems like the answer is incorrect. It's good, it is good. I got 6.56 times 10 to the power of negative 34 plus 8 minus negative 19. So we got 6 meter, 6 times 10. Am I right? You guys definitely are faster than me. I didn't learn math for too many years. So we know 1 meter is 10 to the power of 9 nanometer. So we'll see, this is 656 nanometer. It's very close to 700. So this is why. This is the red line, right? So if you go back, you got this one. We are something in between 600 and 700, but obviously closer to 700, right? We can, further confirm it. So now say hydrogen Unfortunately, we do not have the spectrophotometer. There are some portable spectrophotometers, in chemistry lab, in physics labs. I hope you guys will get the opportunity, in the future to use those kind of calculator to see the emission spectrum of the hydrogen, and you can exactly see the four lines, and then you can read the values of each wavelength. Yeah, 656. Did you see that? This is the absorption spectrum. As we mentioned, the absorption one is supposed to be complementary with the emission. So the wavelength is supposed to be exactly the same, right? This one has no value. I think that one is enough for us to confirm, our calculation. Yeah, this one is good. 656, right? Okay. Any question about the example I just showed you? If no, which is good. Now is your turn to try this practice problem. And I provide the answer here. You need to get the exactly same, answer with me. Just to practice your math and, have a sense about the actually three equations. Someone asked about whether TIA3 calculator is allowed. I'm not sure. Is this one a programmable? If it's programmable, it's not allowed. And some local sections are very, strict with this rule. So don't take the risk.
Sorry, what computer? I mean, what calculator type?
TIA3.
I don't think so. I don't think so.
So it's not, right?
Yeah, but I can check.
Thanks.
Okay, so we need like a specific scientific calculator for it?
No specific. You can use any scientific non-programmable scientific calculator.
Okay.
You guys can let me know if you finish. Okay, Alex confirmed, TI-A3 is programmable. Typically, when I see something like TI, Texas Instruments, pretty much is programmable. But TI, does not produce cheap calculators at all. If your calculator is in between, let's say, cheaper than $50, I think it should be fine, typically. Thanks, Alex.
Mm-hmm.
You guys are pretty much done. Yeah, maybe 30 more seconds. If you couldn't make it done during the class, it's also fine. You can continue after class. If you finish, you can have a look at the equation here. This symbol means proportional. The other symbol means negative plus, negative or plus. Let me do it this way. A few of you are still working, but I don't want to, you guys who finish, wait there. So you guys can working on the problem sets, which is supposed to be a homework.
Are problem sets always going to be due by the next class, or?
No, each problem set is for 3 classes.
Okay.
So basically, the first one will be due in 3 weeks. So I put the due date of each problem set in Google Classroom. There is a document to tell you what is the schedule, what will be the contents in each class, what is the date of each class, and when you need to submit the problem set. So I share the problem set, the PDF in the chat box. You guys can download it right now. I will also put it in Google Classroom later, and also remind you by email. Make sure you get it. And for this one, you don't have to print it because I have no space on the problem set itself. You need to use a white piece of paper and show your work, your detailed work for each question. And then, after you finish all of them, scan it into a single PDF with multiple pages and submit in Google Classroom before the due date. So I will put an assignment there. Does this work for you? Good. Yeah, if you don't know how to do a certain question, leave it there. It's fine, but just label it. So that's the number 1. Leave the space there. Leave the space, for you to do the correction later, right? That's you don't know. And I will share the detailed answer key of each problem set with you guys, and you guys can just quickly have a look. For the first, let's say there are 9 regular questions. They are relatively straightforward because those questions are either from the textbook. Definitely, they are from different textbook. I probably refer to at least 5 to 6 textbooks. But for the middle parts, those questions are from the other exams or competitions. Typically, they are very classical questions, which means they are probably more integrated or harder than the previous questions. So if you cannot solve those questions, no worry at all, okay? We will try to find some time, to talk about the questions. First, definitely, I will share the answer key with detailed explanations. If you still have any question, you can ask your specific question in Google Classroom or later analysis if we have, no matter it's Discord server or WeChat group or whatever you like, okay? And then in the end, typically I will have a long integrated questions. For example, here is from the UK. This is a pretty good question, which is exactly corresponding to the contents we discussed today. So yeah, this problem set is for the first 3 weeks. So you can, schedule your time by yourself. And you cannot finish all of them, after today, because there are a lot of content we didn't learn yet, right? But to feel free, to go forward, right? You can self-study. You don't have to wait. I will kind of pick up a few specific questions, after this class for you to finish. Okay, that is what I recommend for you to finish in this week. I think I should say in the coming week. Okay. Okay. I'm supposing all of you guys finished this question. Any question about this one? You probably will see all of the examples in my lecture notes had answer, but it's only a kind of final answer with no kind of process, no work shown. That is kind of for you to figure out. Okay. Yeah, I think now we can briefly talk about this equation. So 1 over lambda is proportional to negative plus 1 over nf squared minus 1 over n initial square. First, why there is negative, plus minus sign? That depends on, what is your nf and what's your ni. So if nf is greater than ni, which means at this moment you should use the negative sign, right? Sorry, the positive sign, right? The positive sign, because it's from a higher energy level to a lower energy level. Am I right? I'm wrong. It should be negative because it's from higher energy to lower energy. So energy is released. So when energy is released, the delta E is negative. Does this make sense to you? Energy is released, the energy is negative because the system loses energy. So the delta E for the system is negative. So this is why you need to add a negative sign to make, the energy difference positive, and then you can calculate the 1 over lambda. So if nf is smaller than ni, and then it should be the positive sign because it's from the lower energy to the higher energy, basically the absorbing energy. And the absorbing energy, the delta E is positive. Do you need to remember this? No, you just to make sure the delta E is positive, right? So no matter if it's negative, you add a negative sign. If it's positive, it's good. So why is 1 over lambda proportional? Because the right part is delta E. And delta E equals to h times nu. And nu times lambda equals to c. So this is why is 1 over lambda is proportional to the delta E. Makes sense, right? I do not recommend you to try to memorize the equation like this, but you can have a sense about the final conclusion. So basically, 1 over lambda is proportional to the delta E. That is the sense you may get. But you can always use these two equations. Where are the two equations? These two equations. The first one is here. The second one is here, right? To derive the stuff you need. And these two equations typically, let me see, they are provided in the AP Chem exam, but it seems like they are not provided in the USNCO. No, they are not. There are only 3 equations, in the local and national Power 1. As you can see, those are the 3 equations. But the constants are here, so which means you might need to memorize, those 2 equations. But all of the constants, like the Planck constant, h, the speed of light, are all here. Okay. Next is the ionization energy of hydrogen. I think the ionization energy of hydrogen is supposed to be RH over 1 square. This will be the ionization energy of hydrogen. Does this make sense to you? Sure. Because the N final is infinite, right? So which means it's 0 minus RH over 1 square. And you need to make it into positive. So finally it changes into this. I think I probably skipped something and make you guys confused. Let me write it down. So the ionization process basically is from N equals to 1 to N equals to infinite. Am I right? So based on our previous equation, the delta E is supposed to be negative or plus RH times 1 over N final, and final is infinite, square over 1 over N initial, which is 1 square. Am I right? I think it shouldn't be N infinite, it should be just infinite square, right? And then obviously this part is 0. Makes sense, right? So you got, should be RH times 1 over 1 square, which is RH joule. This is the ionization energy of hydrogen. So you completely remove the electron, right, from the ground state. I should emphasize ground state, because if the electron is not in the ground state, obviously delta E is smaller than this, right? Okay. And then there is something called hydrogen-like ions. What does it mean? So basically, there is only one single electron, but it might not be hydrogen. For example, let's say you have helium plus, one electron, right? But it's not hydrogen. And like lithium 2 plus, let's say iron 25 plus, because we know iron is number 26 element. So when it loses 25 electrons, it has only 1 electron left. We call all of those stuff into hydrogen-like ions because the common character is only 1 electron. So for hydrogen-like ions, the ionization energy, or we can say the binding energy, because they are the same with different sign, it's like this. So the only difference, the En means the ionization energy of the electron when it's at the nth layer, right? So it's not necessary to be ground state anymore. If it's not ground state, let's say it's the N energy level, the equation change into this. So the only difference is delta E equals to 1 minus RH 1 over infinite minus 1 over N squared. That is the only difference, right? So this part is still 0. So this is why finally you got RH times 1 over N squared. So another difference here is for hydrogen is 1, but for others, there will be a Z square. What does it mean? Z is the atomic number. Because for the other stuff, they are not hydrogen, although they have only 1 single electron, but they have multiple nucleus. So the attraction force is getting stronger, right? So this is why the ionization energy is also higher. So we didn't really talk about how we get the equation, just to give you the final conclusion. I think it makes sense too. Maybe I should remove the positive sign, the negative sign in the positive sign, because typically when we say ionization energy, we are talking about a positive value, but it really doesn't matter. Does this equation make sense to you?
Yes.
I have a
Great.
question.
Yeah, go ahead.
Why did we write infinity right there?
because it's ionization, right? Ionization means remove the electron from a certain energy level to the infinite place to completely remove it. If you go back a little bit, we talk about this, right? From n equals to any value to here, this process kind of remove the electron completely. And this process is called ionization, right? So this is why you have the infinite square here, either initial or final. Here, I think it's supposed to be final, right? Okay, so the difference between hydrogen and hydrogen-like ions is the Z square. For hydrogen, the Z equals to 1, so Z square is 1. But it is not hydrogen, the Z is not 1, right? Great, almost time. And we are done. We finished, our, planned, stuff. We have one example left. I think you guys can try it as your homework. Basically, this is a listen 2 plus, which means the Z is 3, but is a hydrogen-like ion. And next class, we are going to talk about why we want to emphasize hydrogen-like ions, right? If there are multiple electrons, what will be the situation, right? So leave this question as your homework and check Google Classroom for the questions in the problem sets, which you are recommended to work. If you still have time, I will recommend you to do some reading because next class, we are going to talk about the quantum mechanical model and also the electron configuration. So the difficult points will be the shape of the orbitals and also, the nodes of the orbitals and the different ways to express the different orbitals. Yeah, that will be our next class. In the third class, we are going to mainly talk about the periodic table, the periodic trends, and a few, random stuff, including the ionization energy, the trends, the electron affinity, the electron activity, different definitions, the PES, photoelectron spectroscopy, the inner pair effect, and a few random stuff like the diagonal relationship. Are you guys clear about what will be covered in the first 3 classes, including today? I think today you are quite clear. And next one, we'll mainly talk about the 4 quantum numbers and the orbitals. In the last class, the third class of the responding to the first problem set, we're going to talk about the periodic table, the periodic trends, and a few other stuff. And then we pretty much finish the atomic structure. And then for the 4th, 5th, and 6th class, we are going to talk about the advanced topics in chemical bonding. And then for the third, 3 classes, right? We kind of basically classify our schedule by 3 classes. For the third 3 classes, we are going to move to talk about gas, liquid, solid, phase change, and IMF, intermolecular forces. And hopefully, if we have time left, we can talk about stoichiometry and also descriptive chemistry. That will be the whole season. I hope, if you guys have a clear idea about, what we are going to talk. That's it. Feel free to let me know what's your feedback, right? You want to be a little bit more challenging, or you want to be a little bit, slower. We will try to, match the majority of the class, right? And then work on your problem set. Let me see. Do you have anything to say, Alex?
Not really.
Okay, thanks. Do you guys have any last minute question?
Yeah, how likely is it to have an iron 25 plus ion?
It's it's definitely not likely. Just to give you an example, but since we know we have the successive ionization energy, the first, the second, the third, so theoretically we can remove the electron one by one, right? And we can even measure the ionization energy of each successive energy, ionization energy, right? We can measure all of them. And then that kind of stuff will be useful for us to figure out, how many valence electrons are there. It's here, right? I think probably you guys are familiar with this table. Let me see. Any other question for you guys?
Wait, so for the ionization energy of hydrogen-like ions, is N always equal to 1?
Not necessary. So if it's ground state, N is 1. But if it's in an excited state, it's not 1. So this is why, our final equation actually is this one. Give me 1 second. Our final equation is here. It's En equals to RH over N squared. That means the energy is ionized from a certain excited energy level to the infinite place. Because the infinite place energy is 0. So you can always start from any value of N. Does this make sense to you? Okay. Yeah, that's it. I think from my perspective, from my side, I think the class, ran pretty well. But what I want to remind you is you probably realize, it's not so hard for me to follow. That's because I'm an experienced teacher, right? I make the class easy for you to understand. So I think later you guys will realize it's not so easy for you to solve the problems in the problem sets. It doesn't mean the questions in the problem sets are harder than what I used in the examples. They are pretty much the similar level. But definitely those questions from the other competitions should be a little bit more challenging. But still, they are in the same level. So this is why you always need to practice. Otherwise, the results of the class definitely will be halved or even, not as good as you thought. So please take some time to work on the problem set. And I will see you at 8 o'clock next Sunday, right? Eastern time. And don't forget to finish the survey. I think Alex will send the survey to you, I think tomorrow, right? Just a few minutes for me to know a little bit more about you guys. And I try to, better support you. Okay, guys, bye-bye.